Back in the 1800s, it was known that for certain samples of gases, upon the addition of energy, the gases would glow. I have some tubes of gas here, and I can add electrical energy by touching a Tesla coil to them, and that certainly works. But we're going to do it under a little bit more controlled atmosphere by putting the tubes into this housing here. For example, in there now is a tube of helium, and if I turn it on, it glows. And if we look a little bit closer, we can see it glowing a characteristic peach color. With the lamp off and unplugged, we can take the helium tube out and replace it with a tube of argon. Starting up the lamp again, we'll find that it glows a different color. In this case, it's more of a darker blue purplish color. Next, we'll try neon. This gives the characteristic orange color of a true neon sign. Finally, we have hydrogen. The color there is dominated by a pinkish red, but you can also make out a little bit of blue in that as well. We could analyze this emission further by splitting the colors apart using a diffraction grating or a prism and determining their individual wavelengths. But what does all this teach us about chemistry and atoms? If we take the light emitted from these gas discharge tubes, as shown here for hydrogen, and split it into its components, we find that the elements don't emit every color, but only emit certain wavelengths. This is called an emission spectrum, sometimes referred to as a line spectrum. The emission spectrum of each element is unique and can be used to identify those elements. For example, determining the wavelengths emitted by stars, astronomers have identified elements contained in those stars. In fact, helium, named for the Greek sun god Helios, was first identified by its characteristic emission from our own sun. The wavelengths for hydrogen were known in the 1880s, but scientists were puzzled as to how the numbers relate to one another and why it should be this way. In the 1880s, Johannes Rydberg came up with an empirical relationship between the wavelengths for hydrogen. It is empirical in that it was not based on any theory. He simply took the numbers from the experiment and found an algebraic formula that would reproduce them. It turned out that 1 over the wavelength, which we know is proportional to the frequency, equaled a constant times the quantity 1 over 2 squared minus 1 over n squared. As n was changed from 3 to 4 to 5 to 6, he could set the constant and reproduce the wavelengths in the visible portion of the spectrum. Other lines from hydrogen were discovered in the ultraviolet and infrared portions of the spectrum, so a more general equation can be written where the first n low, is simply a smaller number than the second n high. It was found that this equation could be applied to other chemical species that have 1 electron, such as a helium 1+ ion. After the relationship between energy and frequency was determined by Planck and Einstein, the Rydberg equation could be rewritten for energy. In this equation, Z is the atomic number of the element, which of course equals the number of protons in the nucleus and the charge on the nucleus. H is Planck's constant, and R sub h is called the Rydberg constant for hydrogen. While this equation looks complicated, it's relatively easy to use, since the three terms in front of the brackets are constants for a given element, and the n values are just integers. Note that this equation tells us how the energies are related, but not why they are. We'll need a new model of the atom for that. We can use the Rydberg equation to predict wavelengths of lines in the hydrogen spectrum. As an example, let's predict the frequency and then the wavelength for the line when one n value is 4 and the other is 2. We start with the general equation for frequency. We need to be given the constant, which is 3.290 times 10 to the 15th power. Substituting in the values of 2 for n low and 4 for n high, we find a frequency of 6.169 times 10 to the 14th reciprocal seconds. If we want to know the wavelength of this light, we can use the relationship between frequency and wavelength. Solving for lambda, we get c over nu. Given the speed of light as equal to 3 times 10 to the 8th meters per second, and using the frequency we found before, we calculate a wavelength of 4.86 times 10 to the minus 7th meters. To convert to the more familiar nanometers, we note that 1 meter equals 10 to the 9th nanometers. Using this as a conversion factor, we find a wavelength of 486 nanometers.